Well, he took it. It's my great pleasure to introduce my elder sibling, my academic brother from Rutgers, now back at Rutgers, Matthew Young, who will finish off his lecture series on moments of L functions.
Yeah, thanks, Roman. Yeah. Yeah, just so everyone knows, Roman and I we were at Rutgers together. And I graduated, I got my PhD in 2004, and you were what, like 2 years after that, Roman? Yeah. And then, so then I've been away and now I'm back. So it's like a 20-year gap in between, but now I'm back at Rutgers. Great. So okay, I have to share my screen on my tablet. So let's do that. Okay. So this is just like how I was teaching classes during the pandemic. So it's all kind of coming back to me. So okay, so last time, yeah, I have to see what we finished with. So we were talking about we talked about amplifiers. We talked about the Peterson formula a little bit, and different kinds of families of L functions. And so now, okay, I promised that on Friday we'd talk about moments with GL2 families. So let's make sure to fulfill that promise. So let's start a new page here in the notebook. Okay, so right, so we want to talk about some GL2 family moments. This has become like quite an industry. So there's like a vast amount of research in this area, and so if you're new to the area, it can be kind of like overwhelming with how many different papers there are. So I wanted to, like, as a guide, like point out some of the important works in this area. So there's a nice theorem of Kowalski, Michel, Vanderkam, where so they studied they looked at the fourth moment. So you look at level P cusp forms. And so they look at the fourth moment. They actually don't need the absolute value sign here if you're at a half. So let's just put in a half, yeah. So they proved an asymptotic formula for this. So this is basically P. Okay, and there's some weights here, like these Peterson weights. So sort of it's 1 over the L2 norm squared of your cusp form. So there's those kind of Peterson weights that are in there, which can be removed, but let's not talk about that. So the asymptotic formula that they got is that this is P times a polynomial and log of P, and then they get some sort of power saving. So by power saving, I mean an error term of size P to the 1 minus delta for some delta positive fixed, which is a pretty small numerical constant, and I don't really want to write it down. So there's some delta for which this is true. And this is a long and difficult paper, and but the result is great. And so they get this asymptotic formula with a power saving for this fourth moment so this is a level aspect question. So this is I guess I didn't even say what this was, but like you can fix the weight to be anything you like. So you fix the weight like for holomorphic modular forms of prime level and let the level go off to infinity. Okay, so that's let's see. Yeah. So they prove this, and they actually prove something more than this. So they prove so they actually study more general questions. So last time we talked about these modified moments that we often look at that are useful for lots of applications. And so they actually studied this more general question of F level P. So you sum over the same family, you have the same weights, you still have the L function to the fourth power, but then they put on some kind of so just really an arbitrary Dirichlet polynomial. So you have some coefficients, a sub L, lambda f of L, squared, and we call this thing, let's call that a of f, capital A of f. And they actually get an asymptotic formula for this. And it's for L less than or equal to p to the, I don't know, delta prime, for some delta prime, for some delta prime fixed. So the idea is like, okay, if you can get a power saving, if you can get an asymptotic formula with a power saving, then you can probably put on this kind of Dirichlet polynomial, increase the difficulty a little bit, but you've got some room, like you understand what's going on. The main term is coming, like you kind of understand the main term, and if you put on like these extra weights coming from this this Dirichlet polynomial, you can still handle the main term. You can still get the asymptotic formula for that. The shape of it changes a little bit, but you can still work that out. And since you've got this power saving error term p to the 1 minus delta, you've got some room to sum this thing up over L's and still get an asymptotic. And so that's the rough idea. And so from this, like they make various choices. So for example, they take a of f to equal a mollifier, and then they can get non-vanishing results, like positive percentage non-vanishing results. And then they can also take a of f to be equal to an amplifier. And then they can get subconvexity results. And this paper is just filled with lots of nice applications of these results, and it's just a great paper. So this is a good paper for students to study if you want to learn about some moments. So this was just one example I wanted to mention. So this is example one, I guess. This is a list of it, so we've got some examples. So here an example is like a really long paper that appeared in a top journal. So another example, so this isn't technically a GL2 family, but it actually is connected to a GL2 family. So there's a famous result of Heath Brown, I think from around 1978, if I remember the date correctly. So he got an asymptotic formula for the fourth moment of Riemann zeta function. So this was the first time that there was an asymptotic formula with a power saving error term. So in his case, he got so it's the main term is t times a polynomial in log of t. So we saw I think we saw the other day that this should be like log t to the fourth as the power. Yeah, we actually like I sketched out the how you could get a lower bound on this, and how sound of Ramanujan also proved an upper bound that's not far off from this. So we know that this polynomial is degree 4 here. Like it's not too hard to see that it's relatively easy to see that it's degree 4. But then here he got a full main term, so that he extracted like a full polynomial of degree 4. You really don't want to write it down. It's a complicated polynomial. And then a power saving error term. And then this was later improved. So the state of the art, I guess, to put it this way. So there's the state of the art is due to Motohashi, maybe around 1995. Well, okay, so maybe I should. Yeah, okay. So there's okay. I want to talk about Motohashi, but like he might technically not have been the first to get this result, but this is a consequence of his result. So you get the same polynomial, and then this 7/8 he can replace by t to the 2/3. And this is a consequence of a formula of his that I want to mention shortly. Okay, so this is a GL1 family, but it turns out it's related to some GL2 families, as I want to explain. And then third example, so this is a famous result of Conry and Ivanius. And this is around the year 2000, like 2000. Okay, I'll just put it like these approximation signs. So I might be off by like a year or two here, but it's not too far off. So here, let's take chi sub q to equal the Jacobi symbol. So it's a quadratic character, and some particular q will be odd and square free. So that means this chi q is a primitive quadratic Dirichlet character of odd conductor. And so they proved that if you sum over f these level q cusp forms, and then you look at the twisted central values, so you take everything of level q, or really like level dividing q, and twist it by these quadratic characters, then you can look at the cubic moment of that. And then they also have a part where you can look at the sixth power of just the Dirichlet L function all by itself. And this is a case where we don't have an asymptotic formula with a power saving, but we just have a good upper bound on it. So the upper bound is q to the 1 plus epsilon. And okay, and so this implies, so these central values are okay. So maybe I should, before I put the implication sign. So it's a fact, a deep fact, that these central values are non-negative. And this is like the main input here is a formula of Waltz-Bouguer. Did I spell that correctly? Hopefully I spelled the name correctly. So these central values are connected to the square of a half integral weight. The Fourier coefficient of like the qth Fourier coefficient of a half integral weight modular form in the Shimura correspondence, and so that will give you the non-negativity. Yeah, so these are known to be non-negative, but let's not get too much into that side of things. But these are known to be non-negative, and so then because of that, you can drop all but one term, and so this implies, so this actually implies two subconvexity results. One for the GL2 twisted L function, so the bound is q to the 1/3, and then the plus epsilon, which we should think of as q squared to the 1/6 plus epsilon. I guess there's slightly different epsilons from one line or from one to the next. But anyway, so here the conductor is q squared. And so this is a Weyl exponent. So the Weyl exponent is this 1/6. And so they get so convexity is exponent 1/4. Here they get 1/6. And they also got that for the Dirichlet L function, that's bounded by q to the 1/6 plus epsilon, which again is the Weyl exponent. And this was the first time that we had a Weyl type subconvexity bound for Dirichlet L functions for quadratic characters. So then somewhat recently, Ian Petro and myself generalized this. So I guess we realized that you can look at a sort of variant on the Konrad-Navanian family to get more general characters. So what you do is you look at f level q, and you want to look at modular forms that transform, like have a Nebentipus character or central character, which is chi bar squared. And then you look at L/2 f twisted by chi. So if chi is quadratic, so here chi is let's say primitive mod q. Okay. So if chi is quadratic, then this chi bar squared is the identity, and so you get trivial central character modular forms. And so that's why, like in the Konrad-Navanian result, they didn't say that at all. And so that was something that we were missing, I guess, as a community. We were missing that, like, really that this is like maybe the right generalization of the family of Conry So you take this family, and then you also can look at the sixth power, absolute value of the sixth power of the Dirichlet function, and we proved the bound that this is bounded by q to the 1 plus epsilon. This was spread out over 2 papers. So the first paper, so we had 2 papers. So paper number 1, which wasn't our first paper together. We've written a few series of papers together, but so paper number 1 was that so we did this where Q was cube free first, and then paper number 2 was general Q. We extended it to general Q. And I might try to say more about how this comes up later. But then this has this nice application that just for the Dirichlet functions, that we get the bound q to the 1 over 6 for any chi mod q. So Konrad had the only quadratic characters, and so now we have this for any characters. So just for context, I guess, I don't know if this has been mentioned in some of the other lectures this week, but there's this famous result of Burgess from the 1960s that that L of a half chi is bounded by q to the 3 over 16 plus epsilon. And that's what we call the Burgess bound. So this exponent 3 over 16 comes up in lots of problems, not just for Dirichlet functions, but for some GL2 problems too. And so this Burgess bound is 3 over 16, and it hadn't really been improved until Konrad came along for quadratic characters. Excuse me. So okay, so I'll want to talk more about this cubic moment result a little bit later in the lecture, but we'll set that aside for now. So another thing to mention, so there's this result of Motohashi. So returning to the result of Motohashi, so you can, if you take Motohashi's result, you can actually turn it into a short interval result. And then the bound is t to the 2/3 plus epsilon. So Motohashi implies this, but actually this result that I just stated here is a much older result of Ivanets from around 1980, I think, 79, 80, something like that. So Ivanets did not get the main term with the polynomial and log t and all that, but he got a good upper bound on this fourth moment of zeta on a short interval. And okay, and there's a technique for turning these integral moment bounds into pointwise bounds. So you can actually use this to prove that zeta to the 4th as a pointwise bound is also bounded by, I guess, 1 plus t to the 2/3 plus epsilon. And then that implies that zeta of a half plus it is bounded by t to the should be 1/6 plus epsilon. So again, this gives you the Weil bound. So one of the reasons why we call it the Weil bound, why it has a good name, is that it comes up all the time. There's lots of different ways, at least for certain L functions, like the zeta function, there's lots of different ways to get to the Weil bound. And so it just reoccurs all over the place. So if you're interested in how you convert a moment bound into a pointwise bound, I think just for purposes of time, I won't really be able to get into that in this lecture, but this is explained in, so there's a paper of so you look at Heath Brown So Heath Brown has this paper on the 12th moment of zeta function. So this explains very clearly how to go from moments to pointwise bounds. And then this is also in the book by Titchmarsh. If you want a book reference instead of a paper reference, this is in Titchmarsh's book on the zeta function. I think Heath Brown might have added that. So Heath Brown revised the book of Titchmarsh at some point. Like it's like a second edition, and so he might have added that material in the second edition. Okay. So right. Okay, so let's next. I wanted to return to say more about this result of Motohashi. So he has so he wrote a paper on this, but there's also a treatment. He has a nice treatment of this in his book. So he has this book called The Spectral Theory of the Riemann Zeta Function. And I guess the main purpose of the book is to prove the following theorem. So, okay, so you take some sort of a nice function. I forget what the conditions are on G, but it's like, at the very least, it's a smooth function with rapid decay. It might need to be holomorphic in some strip. But you might think of like a Gaussian. So Gaussian is going to be okay for this theorem. And so then what does he prove? So you take the integral of the zeta function, absolute value to the fourth, and you integrate it against G. So you can think of G as like a smooth approximation to the characteristic function of an interval. And then, so this is like a smooth version of the fourth moment of zeta, where saying that you're integrating from t to 2t or maybe t to t plus delta is encoded by G, this lowercase g. So G can depend on various parameters here. And okay, so he gets an exact formula for this. And the exact formula has the following shape. So there's sort of some main terms that I don't want to write down exactly what they are, but like if you remember, I said there's a main term, right? There's a polynomial in log of t, and so you've got to have that somewhere. Then there's like a dual moment. So he gets a sum over f, level 1 Moss forms. Okay, and then it's the central value. So it's like the cubic moment of the central values of these L functions. And then there's some kind of integral transform of G. So I'll just write it like G check or something of T sub f. So T sub f is the spectral parameter of the Moss form. So it's encoding the Laplace eigenvalue of the Moss form. The T sub f is the parameter that occurs in the gamma factors. There is also a sum over f holomorphic. So there's a sum over those holomorphic forms. You also get a cubic moment there. There's some sort of other integral transform depending on the weight of f. So k sub f is the weight. And then you sum over the weights. And then there's a component that's related to the Eisenstein series. And then this thing turns out to be a sixth moment of zeta, but again, times this G check of t. And it's really an exact formula. Um, and just to actually write it down precisely, it takes up a page. So I'm not going to write it all down. This G check is a completely explicit integral transform. So it's not just like the Fourier transform, but you might chain together the Fourier transform and some other things. He's got hypergeometric functions in there. So it's just a great big, uh, somewhat intimidating expression, but it's completely explicit and yeah, and so that's the formula. So it's a really amazing formula that connects. So we call this like a spectral reciprocity formula, and it connects two different families of L functions. So on the left-hand side, what we're starting with is a degree 1 L function. So this is the fourth power of a degree 1 L function. And then you do various transformations, and you arrive at eventually this dual moment, which is this is the cubic moment of degree 2 L functions. So when you cube a degree 2 L function, you end up in total with a degree 6 L function. So the degrees of these L functions are completely different, right? It starts out degree 4, and then on the other side is degree 6. So it's just they're living in completely different worlds. But nevertheless, we have this identity. So you might worry that the right-hand side is more complicated than the left-hand side, because at the very least, like we started with the fourth moment of zeta on the left side, and then we ended up with the sixth moment of zeta on the right side. So you might say like, okay, we've reduced to something even more complicated, right? So the sixth moment is more complicated than the fourth moment, but in fact, like you don't really need really strong information about the sixth moment on the right-hand side to say something interesting about the fourth moment on the left-hand side. So it's all encoded in how this G check behaves, and so G check is well, I'll write down actually what G check is in a special case in just a moment, and then you can see why it really doesn't matter very much. So great. So this is yeah. So this is not only beautiful, but it's also useful. So useful too. And so here's and I'm just drawing this from Motahashi's book. So he writes down an approximate version, which is maybe easier to work with. So there's an approximate version. So let's say you pick delta as some parameter between t to the half and t over log of t. So then again, don't trust me on this, so you have to look at his book to make sure that I transcribed this correctly. But so on the left-hand side, so basically he chooses his g as a function of t and delta as follows. So you take a Gaussian, which is basically centered at t. Capital T, and then it's the spread on this Gaussian is like delta. So this exponential basically is saying like t minus t is sort of like less than delta. I'll just put that in scare quotes. It's not exactly true, but essentially this is what this is saying, because if little t minus capital T is less than delta, then this is kind of like near exponential of 0, which is like 1. And so the weight is kind of size 1 near in this window of width delta centered at t. But then once you go like, once you're at like 100 times delta, then you've got like exponential of minus 100 squared, and that's a small number. So really quickly, this thing dies off on the scale of delta. Okay, so this is essentially our choice of G. And then okay, so that's the left-hand side, and then the right-hand side, what he gets is pi over square root of 2t. And then he's got the sum over the Moss forms. And he's got these weights. Okay, I guess I lied when I wrote those down. So there's the Peterson or the Peterson slash Kuznetsov weights. Yeah, and then there's some weight here depending on T as well. Okay, so he's got these Peterson weights. He's got the cubic moment. He divides by the square root of T sub f. And then he's got sine of T sub f. So this is this part's actually this highly oscillatory thing. So it's log of T sub f over 4et. And then he's got another like kind of dual Gaussian. So this is exponential minus 1/4, and then it's delta T sub f over capital T quantity squared. And then he's got some kind of error term, which is size log of T to the 9th. And okay, and so this is a you know, a little easier to get your eyes on this because it's you know, you don't have to try to understand what the integral transform is. Basically, Motohashi worked out the integral transform in this case. And so how to look at this? So the left-hand side, you basically have like little t minus capital T is kind of like less than delta. But on the right-hand side, if you look at this Gaussian, it's like a completely different Gaussian. And the thing here on the right-hand side should say that T sub f basically goes up to T over delta. Because like if delta T sub f over capital T, like once that's bigger than 1, then we're in the tail of the Gaussian there. So that's when the right-hand side should decay. So it converts a short interval moment on one side to kind of like a wide moment, like this is all T sub f up to some bound. And there's like this reciprocal relationship. So the longer you pick delta on the left-hand side, the shorter delta is on the right-hand side. So okay, and so also maybe I should say that so there's the Weil law. The Weil law says that the number of f's such that T sub f goes up to capital T is asymptotic to a constant times T squared. That's just the number of these things. So it grows quadratically in T. Okay. So all right. So this isn't what I would call an early example of a spectral reciprocity formula. It's one of the first ones, and it's maybe the best known spectral reciprocity formula. So great. And if you want to see proof of this, you can read Motohashi's book. You know, it's like a couple hundred pages long. So yeah, so then let's see what this is useful for. So I wanna use this for something. So I want to see how we can use this to get a bound on the short interval fourth moment. So just as a proposition, let's pick some parameter v. So if you take the cubic moment in this family, this is bounded by v squared, or I guess v to the 2 plus epsilon. So this is like the Lindelof hypothesis on average for this moment. In fact, we know the fourth moment. So we can actually do something better. And these are kind of like quote unquote easy moments. And they do not imply subconvexity. So there are some moments where you can drop all but one term and you get a good subconvexity result. And then there are some moments where you don't get that. So if your moment's too low or your family's too big or there's sort of the similar kind of phenomenon. Then in those situations, you drop all but one term and your bound is just not very good. And so that doesn't necessarily mean that that moment is easy. It's not true, or it's not the case that you can completely judge the difficulty of a moment based on whether it implies subconvexity or not. But it's one crude measure here, and in this case, it's really not too hard to get these bounds. So okay, so I want to apply those to Motohashi's thing here. So if you go back to this Motohashi's fourth moment of zeta, so he scaled it. He scaled the left-hand side, so he's dividing by delta. So the interval has length delta, but then he's dividing by delta. So if you just want a straight up bound on the fourth moment of zeta, you have to multiply through by delta. Okay, so Motohashi's formula will say like integral t to t plus delta zeta to the fourth is bounded by, okay, so he's going to get delta, so from the error term he gets delta log t to the ninth. And then from the cubic moment, now he's got delta, he's got the square root of t, right? And then he's got a cubic moment. So basically t sub f goes up to t over delta. He's got 1 over square root of t sub f. He's got the cubic moment. And then he's got some kind of like sine of something. And the sine is, it oscillates, and it oscillates actually very quickly because he's got sine of t sub f times log of t sub f. So this is just spinning around really, really fast. And so it's actually really hard to kind of prove any cancellation. But here you can give up any cancellation. Just give up cancellation, use the triangle inequality. And then the bound that you get will be, so you get delta, let's just say delta to the 1 plus epsilon from the delta log t term, and then using the proposition, so this is going to follow from the proposition that we can bound the cubic moment on average, and we're just going to use that sine is less than or equal to 1 in absolute value. And then there's this 1 over square root of tf, which you can handle just by a simple summation by parts argument. And if I did the algebra correctly, you get like the bound t to the 1 plus epsilon over delta to the 3 halves. Oh, wait, I didn't scale through. So I think it's if you multiply through by the delta, then it's delta to the 1 half. So you get this interesting thing that the bound actually, the left-hand side is clearly increasing in delta. The right-hand side might not be, depending on what you choose for delta, but so you can make delta bigger if you want to, and the right-hand side could actually become better that way. So this happens in harmonic analysis, not too infrequently. And so you actually get the best result if you pick delta to be t to the 2/3, and then both bounds give you delta to the 2/3. So then this gives you t plus t to the 2/3, zeta to the fourth is bounded by t to the 2/3 plus epsilon, which was proved by Ivanitz back in like 1980, as I mentioned earlier. But this is getting at it in a different way using this exact formula. So that's my discussion of Motohashi's spectral reciprocity result. Am I supposed to take a break? Are we supposed to have a break somewhere in the middle here, or do I keep going?
I mean, if this seems like a natural place for you, then we could take the break now. You're within the 5-minute window, so.
Okay, yeah, this is a great time to take a little break then.
Okay. All right, we'll be back in 5 minutes.
Okay.
Okay, Matt, the screen is yours.
Okay. Great. So I wanted to give an outline slash sketch for the cubic moment result that I mentioned not too long ago. So this is one of the more I guess advanced moments that are out there. I mean, so if you want to learn, I mean, it's good to, yeah, okay. If you haven't worked on anything about moments before, it's good to read some of the simpler papers first and sort of build up your uh, skills, I guess, in these things. But I mean, it can also be good just to also jump into a difficult one, and then you can then you're well prepared for just about anything. So so this is one of the more difficult ones, I would say, but but there's a lot of uh, uh, good tools that are applicable in other situations that can be useful to become acquainted with. So okay, so let's just sort of jump right in. So what I want to study is again this family. So this is the family of level Q cusp forms, and these are ones that transform by the character chi bar squared. And I want to study the cubic moment in this family. So you might just think about holomorphic modular forms of this level and that transform with this character. And so the first starting point, or the first step, is to use an approximate functional equation. So these twisted L functions. So basically, we have three sums: m1, m2, and m3. One for each of these L functions. It's an L function cubed. They're all twisted by chi, so we'll have chi of m1, m2. Okay, I don't know if this is a good idea. So yeah, so maybe I want. Yeah, I think maybe I want one of them to be conjugated. And then, so it's like I want to think of this as lambda f of m1, m2, and then lambda f of m3 conjugate. Right. And then there's a weight function here. So in the approximate functional equation, we have this weight function. So it sort of looks like m1, m2 over q squared, and then another one at m3 over q. So the conductor of one of these L functions is equal to q squared. And so the square root of the conductor is equal to q. And so then that means that each of these m variables should go up to q. However, there's this technical thing, which is that we want, so if you just do an approximate functional equation for each of the L functions, you get lambda f of m1 times lambda f of m2 times lambda f of m3, and or maybe one of them you could conjugate just for free. The essential values are non-negative, so you can conjugate one of them. So that's where these conjugate signs come from. But the issue is that like in the Peterson formula, we don't have three Heck eigenvalues, we have two, or Fourier coefficients, however you want to think about it. So we have to use like a Hecker relation to group together two of those. So that's the way I've written it. So I've just grouped together m1 and m2 and made that be sort of one variable. So m1, the product m1, m2 goes up to q squared, and m3 goes up to q, but you should really just think of each of these m's as going up to q. Okay, so that's the first step. So this is just writing down the approximate functional equation. The gain here, or the reason we want to do this is we want a essentially finite formula for the L functions inside the critical strip. And so this accomplishes this so that we really do have a finite sum. I mean, technically it's an infinite sum, but it decays very, very quickly when like once the m's are sufficiently large that this weight function v is small. And so the contribution, like when you're off in the tail, is just very small by trivial bounds. And so as far as this asymptotic formula or just trying to understand this moment is concerned, we can make it finite. Maybe I'll say just in passing that there is another approach to these kinds of problems where you start with an expression. So it's like you start with like not just a central point, but a more general point. So you might look at the L function at a point S, and where S is a complex number, but maybe you initially assume that real part of S is bigger than 1, so that you can write down the absolutely convergent Dirichlet series. And then you have to then try to so you might still do the same kind of sequence of moves that I'm about to show you, and hope that in the end you've got something that has an analytic continuation back to S equals a half. So you do all these identities where it's allowed to be convergent, and then you extend it by complex analysis, like analytic continuation. But anyway, that's another approach, and that people have been successful at that, and you can find various papers that do it that way. So, for example, Motohashi does it that way when he in his fourth moment paper. so he does this analytic continuation technique. If you're going to do that, you have to be very diligent about keeping. You need to keep identities throughout the whole thing. You can't use any approximations anywhere because you need, analytic continuation. So you can't start doing any approximations. You can ruin the analytic continuation argument. Okay, but anyway, so this is our formula, and then we have a Peterson formula. So the Peterson formula. The Peterson formula says that if you sum over F level Q and character chi bar squared, and you put in the weights. So maybe I should put in the weights, these Peterson weights. So these are just the weights that you put in to make the Peterson formula work. And then you have lambda F of M, lambda F of N bar. So one of them you have the complex conjugate sign on. So that's why I wanted to conjugate one of these things above. And so this is equal to, so it'll be like Q times the delta function that M equals N plus, oh man, some kind of constant that really doesn't matter. And then I just multiplied through by Q to normalize things. And then anyway, you get a sum over C congruent to 0 mod Q, and then it's a twisted Klosterman sum. And then it's multiplied by a Bessel function. And it's the weight k minus 1. So it's the j k minus 1 Bessel function if on the left-hand side I have weight k. Okay, so that's the Peterson formula that you can find like in Ivanius's book, The Topics in Classical Automorphic Forms. He derives this formula. And it's not too hard to derive the Peterson formula. It's a more work to do the Kuznetsov formula, but I'm only for this lecture, just to make things simpler, we're only doing the holomorphic forms. So we only need the Peterson formula. Okay, so now after applying the approximate functional equation and the Peterson formula, that implies that our cubic moment is equal to kind of a diagonal term plus the sum of Klosterman sums term. So this diagonal term, that's what we get from the delta M equals N term. So this is going to look like Q. We have our sum over M1, M2, and M3. The diagonal coefficient, or the diagonal, the delta part is saying that M1, M2 is equal to M3. Oh, did I forget my characters? No. Okay, so then I've got chi of M1, M2, chi bar of M3 over square root of M1, M2, M3, and then our V functions. And so notice when M1, M2 equals M3 that these characters basically just cancel each other out. And then this just, you can bound this by a kind of harmonic series type of sum. And so this, you get a bound of Q to the 1 plus epsilon. And if you wanted to work harder, you could derive an asymptotic formula for this. But that's not really going to help in any way because we can't, our upper bound on S is also going to be of size Q to the 1 plus epsilon. And so if we could prove S was like a power saving smaller than that, then it'd be worthwhile to develop the asymptotic for this diagonal term. But unfortunately, we don't know how to improve on that. Okay. So this bound is okay. This is what we're looking for, size Q to the 1 plus epsilon. So it's almost always the case that the diagonal term is quite simple and easy to handle. And the hard part is bounding the sum of Klosterman sums part or the off diagonal part. Okay. So just to write it down, the sum of Klosterman sums part. We've got our Q out front. We've got our C congruent to 0 mod Q. We've got our M1, M2, and M3. We've got our characters, chi of M1, M2, chi bar of M3. We've got these things, M1, M2, M3, and then we've got our twisted Klosterman sum. And then times our Bessel function. I'll just write it like J of dot, just for shorthand. Okay, so that's our, zoom out a little bit. So that's our sum of Klosterman sums part. This is the thing that we need to study, and we need to get, we need to bound this. If you just like plug in the Bay bound and just add everything up, you're way off from Q. I forget what bound you actually get from plugging in the trivial bound, but that's usually like the first thing you try is just say like, okay, what happens if you plug in the trivial bound? For everything in sight, like just put in the triangle inequality and bound everything with absolute values. That's what I consider the trivial bound. So if you do that, you're way off from Q. You know, maybe it's Q squared, maybe it's Q to the 2.5. I forget. But you're way off, and so that shows that you need to prove that there's a lot of cancellation in the remaining sums in order to get the bound that you want. So it's a good idea to sort of keep track of how much more cancellation you need to prove in order to get the result that you want. So okay, so one pretty standard technique here that's useful is to apply smooth dyadic partitions of unity to all the variables. So you apply this to C, you apply this to M1, M2, and M3. And let's say C is of size capital C, and then each of the M variables is around N. And then the main part is to study when the variables are kind of around size P. So typically, the main range of C to worry about is when the Bessel function has size 1. So it's when like your square root of M1, M2, M3 over C is kind of like size 1, i.e. this would mean that C is of size n to the 3 halves, which is like P to the 3 halves. And so C is, or sorry, Q. Okay, what happened to I guess P is Q. P became Q somehow. Okay, so that's Q. And then Q to the 3 halves. And C is like, or little c is Q. So C is a multiple of Q. So C would be, let's say, Q times R. And so then this means that R is of size square root of Q. This is not really like a rigorous statement, but it's a good rule of thumb. So it's a really good rule of thumb when you do the Peterson formula to study the ranges of C where the Bessel, like the argument of the Bessel function is size 1. This is just something I guess you get from experience. And I don't know any like real rigorous statement saying like you only need to look at that range, but just in practice, like that's the main case. Okay, this is just some heuristics to have in mind. And then the next main the biggest savings comes from one move, which is Poisson summation. So we're going to apply Poisson summation, in 3 variables, all of M1, M2, and M3, and we're going to apply it mod C. So we have a like an arithmetic function in terms of M1, M2, and M3, namely this product of characters, so chi of M1, chi of M2, chi bar of M3, times this Klosterman sum, or twisted Klosterman sum, which is also periodic mod C. So chi is periodic mod Q, and the Klosterman sum is periodic mod C. And C is a multiple of Q, and so in total, we have a periodic function mod C. So the fact that the reason we were able to do this mod C is that C is congruent to 0 mod Q, and chi is mod Q. So there's this nice compatibility between the moduli of the Dirichlet characters and then the moduli that appear in the Peterson formula. Okay, so right. So what's Poisson summation? Okay, so I don't know, probably you saw this in some other lectures or might have seen it somewhere else, but I mean, I can't really derive everything. So the Poisson summation formula applied to these 3 variables. And then we've got this J-Bessel function. So this is going to say this is equal to a dual sum over N1, N2, and N3. Let's say those are the dual variables. And then I'll just call this S hat of N1, N2, N3 times J hat of N1, N2, and N3. So S hat is this is the finite Fourier transform of the arithmetical part. So it's 1 over c cubed, that's just a scaling factor. And then I sum over x1, x2, and x3 modulo c. So it's chi of x1, x2, chi bar of x3. And then it's the Klosterman sum. So I'll just actually write out the definition of the Klosterman sum. So the Klosterman sum, okay, I don't think well, yeah, I do. Okay, so the star means that we're running over integers t coprime to c. So it's chi squared of t, and then it's e sub c of t x1, x2, plus t bar x3. And then I'll just try to squeeze this in so I don't need to scroll out. So then it's e sub c of, I think I want a plus sign. So this should be n1 x1 plus n2 x2 plus n3 x3. So this is just the finite Fourier transform of my sequence. So the chi of x1, x2, chi bar of x3, the chi squared of t, e sub c, tx1, x2 plus t bar x3. That's our function, that's our s. And then we're taking the Fourier transform of that, so that means we have to multiply it by an additive character. So that's s hat. And then j hat is just the integral Fourier transform. So this is going to be an integral over R3. It's my J-Bessel function evaluated at 4 pi square root of x1, x2, x3 over c. And then it's e of minus n1 x1, or e sub c minus n1 x1 minus n2 x2 minus n3 x3. And then we've got like our v functions and all that good stuff. And then this is integral over the x variables. So this is the integral Fourier transform of our weight function, which involves the J-Bessel function and like all the various bump functions that occur. So okay, so now we're gonna compute everything in sight. So S hat, like for number theory, S hat is the more interesting part. So let's try to so for S hat. So I don't know. I personally find these kinds of calculations pleasant. It's here's this 4 variable character sum. I just find it fun to try to calculate these things. Sometimes it can get tedious and there's like some nuisance things that occur, but overall, I think it's fun, and there's no substitute for just doing some of these things yourself. So so that's for the in the sum over S hat, like we want to try to evaluate it as best you can. And one thing you might look at is like the sum over x1. So if you just look at the sum over x1, this is the sum over x1 mod c, and then if you just pull out all the x1 components, you've got chi of x1, and then you've got e sub c of x1 times something, and the something is tx2 minus n1. Okay, and chi is mod q, just to remind you, chi is mod q, and c, let's say c is q times r. And this thing gets it can get messy, but if you are willing to impose some mild assumptions, then the evaluation can be done like a little bit more efficiently. So right, so the way I like to do this, so we've got this mismatch between the periods. So the additive part is all of mod C, but the multiplicative part is only mod Q. And so these are different moduli. And so so we want to play those off each other. So there's kind of like a part of C that has nothing to do with Q, kind of like the R part. And that's solely an additive character. So that part should we should be able to leverage that. So let's see. So let's write x1 as u plus qy, where u is going to run mod q, and y is going to run mod c over q, which is r, right? C over q is r. And so if you do that, then our sum over x1 becomes a sum over u mod q. We'll get chi of u. So chi of x1 is the same as chi of u because it's periodic. And then we'll have e sub c of u times tx2 minus n1. Oops. And then we have a sum over y mod r. And then it'll be e sub r of y times tx2 minus n1. Now this inner sum is just by orthogonality of characters. This is equal to r times the delta function that r divides tx2 minus n1. And then, okay. And then once you know that that's divisible, then you can write the inner sum over u. This will just become a Gauss sum. So this becomes e sub q of u times tx2 minus n1 over r. And then this is, then you can evaluate this as a Gauss sum. So chi is a primitive character mod q. So this becomes r, the Gauss sum of chi, and then you get a chi bar of tx2 minus n1 over r. So this is like kind of the building block of how you can compute these sums. So we can do this in x1. So do the same for, let's say, x3, the other variable. And right, and then what we have left over, it will be two variables, t and x2. And if you're willing to just trust me, to make a long story short in the calculation here, making a long story short in the calculation, under some mild assumptions, for example, so if n1, n2, n3, and also r, if all those things are coprime to q, which is not too hard to ensure if q is a prime, for example. So you might, on a first pass, you might just assume q is a prime. That might be the most interesting case. And then it's not hard. Either you're divisible by prime or you're not. And if you're divisible by prime, like that's really cutting down just the number of, being divisible by prime really cuts down just on the cardinality of the set of integers that you're looking at. So if this happens, then so following these like kinds of simple-minded evaluations of these character sums, this should become the following. So you get this additive character that sort of factors out front, And then you have a double sum left over. So let's say those variables are u and t mod q. So you get chi of t plus 1, chi bar of t, chi of, let's see, so chi bar of u plus 1, chi of u, and then times, then you have times an additive character. I'll just write it on the second line here. So it's n1, n2, n3 r bar times ut minus 1. Try to make those parentheses more clear. So ut minus 1. Ah. Okay, so it looks something like this. And so we've evaluated it out as best we can. And then now we're sort of stuck. So we've got this 2-variable character sum left over. It's like chi add a linear fractional transformation of t, and then chi bar linear fractional transformation of u. And then with this extra additive character thrown into the mix. And then I don't really know how to evaluate this any further. It's just any kind of like change of variables that you do just it sort of either gives you the same thing back or something that looks more complicated. So this is sort of the best we can do. So this is like the first thing, you just try to simplify it as much as you can and then stare at it and see what you can do with it. So this is the best that we know how to do for S hat. So Roman, what time should I stop?
10 minutes late, 15
10
minutes.
minutes.
Oh, it's
10
up.
or 15 minutes. Okay, I can do that. So then I'll try to just do the big picture. So again, this is an outline. And if you want all the details, you have to read the paper. So J hat is going to be this threefold integral transform. And then you integrate it dx1, dx2, dx3. I saw that Stefan Bayer was giving a series of lectures on exponential sums, which presumably you've looked at things like this then, because if you want to study these exponential sums using like van der Korp's method, then you study the corresponding exponential integral. So this is just a threefold exponential integral, and you can use the stationary phase method to evaluate this integral. Stationary phase method. And just to sort of get to the punchline, this is going to imply that J hat is approximately E of, okay, let's make sure I get this right. So E of N1, N2, N3 over C times sort of a nice function, like a non-oscillatory function. So the oscillation of J hat is completely encoded, or I don't know, all of it is in this E of N1, N2, N3 over C term. So it's this quite fascinating thing that it's like this, you've got this like transcendental function, or I don't know if we call this transcendental. I mean, it's some Bessel function, and you've got some complicated integral thing. It's just like pure analysis to try to understand it. And you end up with this arithmetical function that pops out. Like this E of N1, N2, N3 over C, this is an additive character mod C, but it comes out in the analysis by this integral analysis. And this was noticed by Konrad Ibanez as well. So, but there's this amazing phenomenon, and I'll underline it in green. So this part in green here in S hat, and this thing in green in J hat, they perfectly cancel. So these two additive characters perfectly cancel each other out. And this is a wonderful feature, and it really is important for the for the estimate. So great. So this tells us that our Okay, so our moment, our moment gets transformed into some kind of scalar out front that this is like bookkeeping to keep track of that. And then you've got a sum over n1, n2, and n3. Now yeah, and so then the integral part is it's just sort of a nice function. So a nice function of these variables. Oh, I forgot. So C became a sum over R. And then the part that's left over is the sum over U and T mod Q. Chi of the things, and you've got the additive character of N1, N2, N3 R bar times UT minus 1. Okay. So now, okay. So now we still need some cancellation in this thing, it turns out. So again, I didn't keep track of where we're at here. I mean, the Poisson summation saved us a lot. So the N1, N2, and N3 are now going to go up to Q to the half plus epsilon. So if you do kind of like an integration by parts argument on the integral, you can see when it's small, and basically it's small when these things are bigger than square root of Q. So the original variables, M1, M2, and M3 went up to Q. Now these go up to square root of Q. So that's a lot smaller. So there's a lot of savings just in the cardinality of the set of integers that we need to work with. But that's still not enough to get the Lindelof hypothesis on average for this cubic moment. You can just check, like you'll be off by a factor, and I think the factor is big enough that you don't get anything interesting out. So you need to squeeze out some more cancellation somewhere. So the basic idea next, again, this is going back to covering of onions, is to basically switch from additive characters to multiplicative characters. So we're going to use that E sub q of this this n1, n2, n3 r bar times ut minus 1. I want to switch this to multiplicative characters. So this is 1 over the Euler phi function of q, sum over psi mod q, Gauss sum of psi bar, and then it's psi of n1, n2, n3 r bar times psi of ut minus 1. So we switch to multiplicative characters, and the whole point is like that that's going to separate these variables. So the n variables and the r variable, like those get separated from each other and from the u and t variables. And we only had to do one Fourier inversion. This is Fourier inversion. Oh, was there a question? Okay. No, okay. Sorry. And
Yeah, but if Philippe does want to say something.
Yeah. So just want to say your UT sum is a multiplicative convolution because you have the UT product of two functions. So it's reasonable to if you have a multiplicative convolution if you look at the Mellin transform, you will get a product situation. See, because you have a function of u, a function of t, and then they are connected via ut. So I think this is a reason why they, at least in the ut aspect, that you can think of doing this.
But yeah, well, it's a little bit different. I mean, it's psi of ut minus 1, right? So it's somehow it's the fact that like we get n1, n2, n3 r bar as like a block. So I'm looking more at like the dependence on the n and r variables rather than the u and t variables. But you're right. I mean, it does only depend on u times t, but it's also ut minus 1. So I'm not doing it just to separate ut. You're right. Like it is a convolution of ut, but I don't know. Maybe it's two different ways to see something, which is good. So, okay, so this is going to separate these variables, the n variables, from each other. And so then if you plug this in, I mean, okay, so, and then there is a cost to this change of variables. So like if you look at this in this formula, this separation of variables formula, the left-hand side is an additive character. It's bounded by 1 in absolute value. The right-hand side, if you plug in the triangle inequality, you'll get square root of q. And so you lose a square root of q when you apply this formula. But we're going to gain more of that back. So it's like you pay the price, square root of q price once, but then you gain a lot back. And so if you just plug this in, then this sum s is going to be, and then we take the sum over psi to the outside. So we're going to get sum over psi mod q. We've got our Gauss sum. And then I'll write it as g of chi psi. I'll write down the definition of that, but it's a function of chi and psi only. And then we've got n1, n2, n3, and r. And then we've got these characters, n1, n2, n3, r bar, and then times like kind of a nice weight function of everything in sight. And here, g of chi psi is the sum over this u and t mod q. So it's chi of t, chi bar of t plus 1. So that's like this linear fractional transformation in chi. And then chi bar of u, chi of u plus 1. So another linear fractional transformation. And then psi evaluated at ut minus 1. So that's this two variable character sum that we're left with. Okay. So now we're in the home stretch here. So sum over n1, n2, n3, and r, we're going to write as like just like a standard thing where you write this as an integral of the Mellin transform of our weight function. And then it'll be times the Dirichlet L function. So we'll get L of S1 psi, L of S2 psi, L of S3 psi, and L of S4 psi. That one is psi bar, because that one is like this R variable. Whoops. It's that one. And so you can shift this to the half line. And so this ends up being something like L of a half psi, I guess, cubed times L of a half psi bar once. And so this means that like our original cubic moment, so this says very roughly speaking, cubic moment gets transformed to like diagonal term plus a dual moment. The dual moment is the sum over psi mod q, and it's kind of like L of a half psi. I'll just write it like this. So it's like the L function to the fourth times this g of chi psi times some normalizing constant out front. So this is like another instance of one of these spectral reciprocity formulas, although this is very much not an exact identity, at least the way I've derived it. There are other people that have worked out the exact formula versions of this. But so this is like the dual moment. Okay, so now we call up Philippe and he tells us how to bound g chi psi. So using this trace formula, trace function machinery. And that will imply that g of chi psi is bounded by q to the 1 plus epsilon, at least if q is a prime, or maybe more generally square free. I don't know. I mean, okay, I was asleep. I didn't get to see your lecture, Philippe, but did you talk about this one at all, or no?
Not this sum, but we did complicated sum, which, yeah, now nobody should be afraid, I think.
Okay, good. So, excuse me. So you plug in this bound, and then for this g chi psi, and then we have a pretty easy bound that we have the fourth moment bound. So this is kind of an easier bound, or an easy moment bound. I think I even showed you how to get this upper bound using like we were able to actually derive this on one of the first days of this lecture series. And so then you put, and then this is enough. Now, so this is enough to give you the bound that you want. So you have this strong bound on the G character sum, which is this multivariable character sum. And so that's the deep input from algebraic geometry, I guess. And then we have like oh, I forgot to write the 4 up there. And then we have this fourth moment bound on the Dirichlet function. So this is in the same style of what happened with Motohashi's fourth moment formula for the zeta function. There he started with the zeta function moment, converted it to another moment, the dual moment, so to speak. He had this like this complicated sine function that's oscillating a lot. Similarly here, we've got this G thing that as a function of psi might be spinning around a lot, but we're just going to put in absolute values on that because we don't know how to sort of exploit that, any cancellation from that. And then we get an easy moment on the dual side that we just plug in an easy bound for that. So some of these features are in common with lots of these different moment questions. So there's this nice structure that pops up that is that you see in all these different problems. I guess I should say, like, very briefly, since it kind of came up as like a little loose end. So this works for Q square free. You can actually extend it to cube free. Like this bound on G extends to cube free, but then when you start having prime cube divisors of Q, then this bound on G is no longer true. So sadly, G chi psi bounded by Q to the 1 plus epsilon is not always true for Q equals P cubed, P to the 4th, and so on. So if Q has a prime power at least 3, then it's not always true, and then you have to work harder. And that's, so I mentioned, so Ian Petro and I wrote 2 papers. So the second paper deals with these higher prime powers. So see, so this is it's called like the the fourth moment of Dirichlet L functions along a coset, but just for shorthand, it's the coset paper for such Qs. So if you want to generalize it to all Qs, then we have to work harder. But the overall structure that I showed you is the one that's in the first paper. That's the cube free. Okay, so I think I'll stop here, and hopefully that's about the right time to stop for on your end. I hope I didn't go late, but I'll stop here. Thank you.
Thank you. I don't know if you could hear the applause. I tried to clap very closely.
It always mutes it. I don't know if it's like just my Zoom or what.
Well, it was deafening in this room, so.
Oh, right.
Um,
It's like the Beatles or the Rolling Stones or something.
any questions for Matt? Yeah, okay, I'll run over to Jacob.
Hi, Matt. Maybe I should know this already, but out of curiosity, you say there's not much need to work hard to get an asymptotic in the diagonal term because the off diagonal is, we don't have a better bound on it anyway. Do you is that because the off diagonal contains something of that size, you think, genuinely, or just because we don't know how to bound it better?
Let's see. That's a good question. I mean, it should certainly be like so generally what happens is the diagonal term gives you the largest power of log, and then the other like off diagonal main terms are at least 1 log smaller than that. And so let's see. So for the so I haven't really thought about where all the other I don't know if we should expect a power saving error term here, or maybe maybe it would come from like Yeah, I think it's tricky. Yeah, I think it's very tricky, actually. To try, like if there is a main term trying to identify it. Like Philippe, you and Ian thought about this for a while, right? But I forget what Ian told me about what you all had done.
Again, what?
Like so you had thought about trying to get an asymptotic and like trying to study the like what the main terms might look like on the on the
Okay, so
dual side.
I would bet that the fourth moment twisted by G type psi is small, and but this is so the fourth moment is the pure fourth moment is hard enough, and see we twist by this factor. But I would expect that the term in your last slide would be an error term, and then
Like a power saving error term.
yes, yeah, because your L function are essentially one, and then you have the G type psi which oscillates.
Yeah. So yeah, okay, good. So that suggests that any kind of other main terms would come from like so maybe you have psi being the trivial character. That can sometimes be a source of a main term. Also, when I did Poisson summation, so when you do Poisson summation, you have zero frequency, and I just completely ignored those. And then you have like partial zero frequencies, where like one of the one of the dual variables is zero, but the others are not. And so you have to study all those things. So maybe that would maybe you could identify like the full main term from that. I don't think anyone has done that, but that should be something that one could do.
Still, I have a question because okay, you did not say what is happening from for prime powers, but there you are in a very interesting situation concerning your sum G type psi, because they could be big. So
Yeah.
yeah,
So
that's
that. So we
interesting.
studied that and we figured out exactly when it's big, but but then it can only be big on cosets, on certain cosets that are fairly small size cosets. And so then you can just bound the fourth moment along these cosets, and then you get a good bound on that.
So
So I don't think that would lead to like a weird main term.
a better bound for the degenerate psi, is it a power saving bound, or is it just the
Yeah,
size?
like so if you had Lindelof, then I think you could get a power saving for that kind of stuff.
Okay, anybody else? Okay, if not, let's thank Matt once more. And I'll hand it over to Ritabrata for some comments.
Thank you, Roman. I hope I'm audible there.
Yes.
Yeah, good. Okay, so my job basically is to thank everyone. So thank you. But well, this is not the end. Though the workshop part of the first half of the event, the circle method related topics, comes to an end with this talk. We'll continue next week with the conference. So I'd like to take this opportunity to thank you all, and especially the speakers in the workshop. First of all, I would like to thank Philip for agreeing to deliver the ICTS Infosys Ramanujan lectures. His talks will remain an asset in the ICTS archive for us to visit and revisit in the future. I'm sure our students and postdocs will benefit immensely from those. And thanks a lot to other senior speakers, Balu for his wonderful series of talks on the classical circle method, the wiring problem, and the Goldberg 3', I guess. And Matt for his inspiring mini course on the moment method and other hot stuff. And Stefan for his excellent exposition, as always, in the theory of exponential sums. Right, and yeah, my thanks to our junior band of speakers, Keshav, Vinay, and Saurabh, without whose contributions this workshop would not have been so successful. And yeah, I need I would like to thank the administrative staff at ICTS, especially Raju and his colleagues in the program office. I'm not sure if I should thank someone else in particular, as I'm not there physically, but maybe Saurabh will do that. I'm sure ICTS has taken good care of all of you. From my side, I can say that the live stream on the YouTube worked quite well. I could follow most of the talks. Anyway, some of you will be leaving this weekend. To them, I say goodbye till the next time. And for the others, I look forward to meeting you all next week. And yeah, a big thank you to Saurabh, if he's around, for organizing the first week. And you can take some rest now. Okay, thank you. Okay, thanks. Yeah, back to you, Roman.
And I guess my responsibility as being the last moderator is to also thank the organizers for putting together this wonderful week. Thank you.
Thank you. Thank you.
Oh, Stefan. Oh, Stefan also. Okay.
Yeah. So we would like to thank the organizers for arranging this wonderful workshop in this beautiful environment. Professor Ritabrata Munshi, Professor Saurabh Kumar Singh, and Professor Kummari Mallesham. And also we would like to thank once again all the speakers for their valuable contributions and for the time they have taken. I think it was a very nice mix of different methods from the analytic side and from the algebraic side, reaching from classical methods to very hot new stuff. I think we can all benefit greatly from it. Maybe when we get stuck with some problem, we can remember these talks and find a solution. Yeah, and finally, thanks again to the ICTS for their hospitality. It's always great to be here. We have everything we need. Very clean air, great temperatures, modern facilities, and a silent environment. Yeah. And yeah, then I hope to see a lot of you next week for the continuation of this workshop, so the conference. And happy Diwali, and have all a nice weekend. There's a lot to explore in the neighborhood of Bangalore. Okay, thank you very much.
Okay, thanks all. Thanks all this team speaker for giving such wonderful talk. And I would like to thank audience for sitting for 7.5 hours continuously. And also like to thank ICTS staff for providing such wonderful facilities here. So thank you everyone.